So let Fn be measurable functions. We say that Fn converges to F in measure and the notation for this is Fn goes to F in mu. So this one kind of convergence if for every epsilon positive, limit n tending to infinity of the measure of the set mod Fn minus F greater or equal to epsilon, that limit is 0. Okay, so again you know what this is, set of all x, so set Fnx minus Fx is greater or equal to epsilon, that is the set, so it's measurable, so its measure has to go to 0. So if Fn goes to F in LP mu, show that Fn goes to F in measure. So solution. So let En epsilon equal to the set mod Fn minus F greater or equal to epsilon. Okay. So now integral over x mod Fn minus F power p d mu is greater or equal to integral over En epsilon. You are taking a smaller set and the integrand is non-negative, so you have Fn minus F power p d mu, but on this set Fn minus F is greater or equal to epsilon, so this being to epsilon power p mu of En epsilon. Therefore mu of En of epsilon is lesser or equal to 1 by epsilon power p integral over x mod Fn minus F power p d mu, and you are told that this goes to 0, and consequently you have that this also goes to 0, which is exactly saying that is Fn goes to F in measure. Okay. This is very similar, this kind of argument if you have seen in measure theory or probability theory, something called Chebyshev's inequality, that is almost proved in the same fashion. Okay, so this is the same kind of proof which one uses, and a very useful argument where you use just the fact that the integral, if you take a non-negative integrand, then the integral over the smaller set is smaller. Okay, then 6. Let 1 less than p less than infinity and f be a function from x cross x to r, such that for almost every y you have x going to fy of x, which is f of xy, is p integrable. 1 and 2, since it's p integrable, we can take a norm fy over p, and then if you integrate that x with respect to y, d mu y, and that is given to be finite. Define, so these are the hypotheses. So now define gx equals integral over x f of xy d mu y. Means this is a function of two variables. I am considering x as constant and integrating with respect to y with respect to the measure mu. Show that g belongs to LP of mu and that norm GP is less than or equal to integral over x norm f y p d mu. So solution, this is an argument very similar to our proof of the Young's inequality. So let phi belong to LP star mu. So this is the conjugate exponent. Okay, then mod of integral phi g d mu is less than or equal to integral over x with respect to x, integral x with respect to y, mod phi x, mod f of x y, d mu y, d mu x. So everything is non-negative, so you can interchange the order of integration. So this is integral xy, integral x with respect to x, and then you have mod phi x, mod fy of x, d mu x, d mu y. So this in LP, this in LP star by the Hölder inequality. This is less than or equal to integral over xy, norm fy, p, norm phi p star, d mu x, d mu y, sorry. We have already integrated over x. So this is equal to norm phi p star into integral over x, norm fy p d mu y, and that is of course finite. So given that 1 is less than p is less than infinity, so phi is in p star, therefore this is a continuous linear functional on g so phi going to integral phi g is a continuous linear functional on LP star mu, and therefore this implies that g belongs to LP of mu, and therefore norm GP is less than or equal to integral over x, norm fy p d mu y. Okay, so that is it's just exactly like we did for the Young's inequality. So we use the duality argument and then we do this problem. Seven. Let G belong to CC of R. Continuous functions with compact support in R. Define phi of G as the evaluation at G equal to at 0. So phi G equals 0. Then of course mod phi G is less than or equal to norm G infinity, and therefore this is continuous with respect to the L infinity norm. Therefore by Hahn-Banach there exists a phi in L infinity of R star such that, so phi tilde if you like, such that norm of such that phi tilde restricted to CC of R equal to phi, and of course the norm will be preserved and so on. Okay, show that phi tilde does not come from L1 of R. That is, there does not exist f. Yes, there does not exist f in L1 of R such that phi tilde of G equals integral f of G d mu over x for all G in L infinity of mu. Okay, so this is another proof that L infinity star is not equal to L1, and therefore which implies that L1, L infinity are not reflexive. We gave another type of proof for that. So here we are producing directly a linear functional which does not come from it. Okay, so solution. Assume there exists f in L1 such that phi tilde g equals integral of x f of g d mu dx. In fact, we are talking about r, we are talking about Lebesgue measure, so let me put, I have to put dx. For all g, again, okay, so one more mistake, sorry again, so L infinity. Okay, okay, for all g in L infinity of r. Okay, so now we take gn to be the following function. This is 1 plus nx if x belongs to minus 1 by n 0, 1 nx 1 minus nx if x belongs to 0 1 by n and 0 otherwise. So what is this function? This is a line, this is minus 1 by n and this is 1 by n. This is the value 1 here. So the function is a roof type function, so it's 0 here, it is 0 here, inside it takes this kind of value. Okay, so then Gn belongs to Cc of R. Okay, and you have phi of Gn, the phi tilde of Gn equals phi of Gn because, and that is equal to Gn 0, which is equal to 1. Okay, on the other hand, you have integral over R of f Gn dx mod is equal to integral minus 1 by n to 1 by n only f Gn dx, which is less than or equal to mod Gn is less than or equal to 1, so less than or equal to integral minus 1 by n to 1 by n mod f dx. Now f is in L1 of R and the measure of minus 1 by n 1 by n is 2 by n. The Lebesgue measure is just the length of the interval which goes to 0. Therefore, by absolute continuity of the Lebesgue integral with respect to the Lebesgue measure, we have mod integral over R f Gn dx goes equal to or less than or equal to integral mod f dx minus 1 by n to 1 by n, and that goes to 0. So this goes to 0. On the other hand, you have phi tilde Gn equal to 1, so these two cannot be equal, and that proves the result. So you have a contradiction. Let H belong to Rn, be a vector. Define fh of x as just a translate. So this is f of x plus h. So Lebesgue measure is translation invariant. So f is in LP implies fh is in LP. Translation invariance of the Lebesgue measure. Okay, so that tells you that this is. Now show that if f is in LP of Rn implies that norm f minus fh in LP goes to 0 as h goes to 0. So solution. So let us take, yeah, so we have to 1 less than equal to p less than infinity. Okay. Okay, solution. So let G belong to Cc of Rn. Okay, so this implies it's a continuous function with compact support, so G is uniformly continuous. Okay, so given epsilon greater than 0, there exists a delta positive such that norm h or mod h is the norm in Rn, so mod h is less than delta, implies mod g of x plus h minus gx is less than epsilon for all x in Rn because of the uniform continuity. So norm g minus gh in LP is equal to integral mod g of x plus h minus g of x power p dx, so whole power p, of course. Now where am I going? I should integrate this over all of Rn, okay, but G has compact support and GH support is just translated by H, and H is less than delta, which can be assumed without loss of generality to be less than 1, and therefore the support of these functions will be contained in K plus B01 closure. Okay, so K is the support of G, compact, because this translate of H will be just this, so this will be non-zero indefinitely, will be 0 outside this set, and therefore you have this, and so that is less than or equal to epsilon power p into the measure, which is for us modulus of K plus B closure 0 1, and therefore this implies that G minus GH in LP tends to 0. So this is true for any thing. So now let F belong to LP of Rn. So we have that there exists a G in Cc of Rn such that norm of F minus G in LP is less than epsilon by 3. Okay. Then there exists a delta positive such that norm H is less than delta, implies norm G minus GH power P is less than epsilon by 3. And then what about norm of FH minus GH? You are translating both of these by the translation invariance of Lebesgue measure. This is nothing but norm of F minus G P, and therefore that is less than epsilon by 3. Therefore norm of F minus FH P is less than equal to norm F minus G P plus norm of G minus GH P plus norm GH minus FH P, and each is less than epsilon by 3, and therefore this is less than epsilon for all mod H, norm mod H, let me say, for all mod H less than delta, and therefore that proves the statement. Okay, so as a application of this result, we take F belong to L1 of R, then integral over R e power I omega t f of t dt tends to 0 as omega tends to infinity. So we are taking a complex function. Of course, complex functions, it's the same, the Lebesgue integral, you take the modulus, power p should be integrable. So if you take the modulus, this is f is in L1, e power I omega t modulus is 1, and therefore this is still integrable, and therefore this is well defined. Okay, so now let us define g of omega equals integral over r e power I omega t ft dt. Now you have e power I pi minus I pi, sorry, is minus 1. Okay, e power minus I pi is minus 1. Okay, e power I pi is minus 1, e power minus I pi is also minus 1. So I am going to multiply by minus 1. So minus g omega equals integral over r of e power I omega t minus I pi times ft dt. Okay, and that's equal to integral over r I omega into t minus pi by omega ft dt. And if I make a change of variable, this is equal to integral over r e power, sorry, this is equal to e power I omega t of f of t plus pi by omega dt. Therefore, twice mod g of omega is less than or equal to mod integral over r e power I omega t ft minus f of t plus pi by omega dt, and that is, of course, now if I take the modulus inside, e power I omega t is 1, and then I will get nothing but the L1 norm of f minus f so pi by omega 1, and that goes to 0 as omega tends to infinity, because pi by omega goes to 0, and that is the H translation. This is by exercise 8. Okay, so 10. Let Fn equals chi of the interval n plus 1 in R. Okay. Before this, so corollary to the previous thing, if f is in L1 of R, then integral over, if you take real and imaginary parts of that integral, you have ft cos nt dt tends to 0, and integral over r ft sin nt dt tends to 0 as n tends to infinity. Okay, that's the corollary of the previous exercise. Okay, let Fn is so this sequence is bounded in L1 of R. Okay, it show that it does not have a convergent subsequence. So again, you show that L1 of R is not reflexive. So L1 of R not reflexive. That's another example to show that. So solution: let f and k weakly converge to f. So that means, that is, for every g in the dual space, that is L infinity of R, we have that integral over R fn k g dx goes to integral fg dx. Okay, but what is fn k? So fn k is that is integral nk to nk plus 1 g dx is convergent for every g in L infinity of R, and that's not possible. You can take arbitrary L infinity functions can be arbitrarily defined. With a similar argument we showed for little L infinity, we showed the sequence does not have a convergent subsequence. Okay, we have seen such an argument before, so it's the same argument. So you take G in L infinity R, example, you take Gx equals plus 1 if x belongs to n2k plus 1, minus 1 if x belongs to n2k plus 1 n2k plus 1 plus 1, and 0 otherwise. Okay, so such a thing will alternately give you plus 1, minus 1 and so on the integral, and therefore that integral cannot converge. Okay, so if you compute this, you will alternately get plus 1, minus 1, plus 1, minus 1 for the subsequence, and that is not a convergent subsequence. So you cannot have a convergent subsequence for this. Okay, we will continue with more exercises.